We're going to finish this chapter with an important result concerning nested intervals. It's important because it's a fundamental result, a fundamental part of the proof of the Bolzano-Weierstrass theorem, which we'll talk about when we talk about sequences. But we're presenting it here for two main reasons. The first one is that the style and the rigor that I'm going to use to prove this theorem is very much typical of analysis proofs in general. So this is a good example of what it means to prove an analytical statement. The other one is that it will allow us to reinforce the concepts of supremum and infimum. We prove them using these concepts. The statement of the nested intervals theorem is the following. For every integer n, let in be an interval an be n. This is a closed interval, closed brackets. If the sequence of intervals in is such that the first interval in the sequence contains the second one in its entirety, which itself contains the third one in its entirety, and so forth, then you can find psi and eta are such that, on the one hand, psi is smaller than or equal to eta, and the important part, if you want, the intersection of all these intervals is actually the interval psi eta. Note here that the interval is closed, just as the intervals in the statement are closed. And if, furthermore, the infimum of Bn minus An, that is, the infimum of the lengths of the original intervals, is 0, then psi is actually equal to eta, and the intersection here is simply going to be a point set. Let's take a second to think about what this means. We start with a sequence of closed nested intervals. Their intersection is itself going to be a closed interval. That's the first main result. The second component here, the furthermore part, if it turns out that the lengths of these intervals are getting smaller and smaller, the infimum of all the lengths is 0. We'll talk about what that means in terms of the lengths getting smaller and smaller when we talk about sequences, limits of sequences. Then the intersection here is actually a single point. Before we prove this result, let's see what this looks like potentially in practice. I will say that the intervals in are the following intervals: 1 minus 1 over n and 1 plus 1 over n. So I1 would be the interval 1 minus 1, 0, 1 plus 1, 2. I2 would be 1 minus 1 over 2, so 1 half, 1 plus 1 over 2, 3 halves. I3 would be 2/3, 4/3, and so forth. Now let me draw these intervals here. The first interval is 0, 2. The next one, this is one here, 1 half, 3 halves. The next one will be 1/3, 3/3. You can imagine the next one being 1/4, 5/4, and so forth. So these are all closed intervals, and they clearly form a sequence of nested intervals. Now, I say clearly, there is something to prove here. There is something to be shown. Are you able to show that in contains in plus 1? What does that really mean? Are you able to show that 1 minus 1 over n, 1 plus 1 over n contains the interval from 1 minus 1 over n plus 1 and 1 plus 1 over n plus 1? What would you need to show? Well, you would need to show, for instance, that this number here, this lower end, is inside of the interval in, which is to say that it is going to be greater than 1 minus 1 over n and smaller than 1 over 1 plus n. That's one thing. Then you would also need to show that the upper endpoint of the in plus 1 interval satisfies the same inequalities, and you would technically also have to show that the lower endpoint is smaller than the upper end. How do you show that? Well, you show that by mathematical induction, right? I mean, I'm seeing a bunch of n's and n plus 1s. Well, not necessarily so. You might be able to manipulate the expressions and just show that a specific inequality holds. At any rate, you'd have to show that this is a sequence of closed nested intervals before you can use the nested intervals theorem to conclude that the intersection of these intervals is actually closed interval by the nested intervals theorem. And on top of that, you can show that the infimum of the length, which is to say bn minus an, actually the infimum of 2 over n. Simplify this expression here. This is something that you've already seen how to compute. This infimum would be twice the infimum 1 over n, which we know to be 0. So here, the infimum of the length is 0, so that in fact, the intersection of the nested intervals is actually a single point, not a closed interval. I mean, yes, a single point is a closed interval, but specifically it's an interval that only contains one point. And you can probably guess what that psi would be just by looking at the picture here. It's very likely that this psi is 1. It has to be. Look, 1 is contained in every single one of these intervals. So we know that 1 belongs to in for every n. Hence, 1 belongs to the intersection of the in's. And since the intersection only contains 1 point, you don't have a choice. Psi has to be equal to 1. I'd like to warn you about something now. Give you a warning signal. Be careful. You can only use the nested intervals theorem. In fact, that's also true for any theorem you want to use if the hypotheses are satisfied by the example that you're considering. If you look at a series of intervals which are not closed intervals, that are open intervals, which I believe in English is denoted with round brackets instead of square brackets. In French, you use square brackets, but the opposite direction, opposite orientation. Every once in a while I might slip and write them as I would in French. And when that happens, keep in mind that I'm really talking about the open interval here. At any rate, we have this sequence of open intervals, 1 minus 1 over n, 1 plus 1 over n, not the same intervals as the one we had in the previous example. These intervals are also nested. The nth interval contains the n plus 1 interval. The reality of it is these inequalities that you were showing to be true in the previous slide, when we were showing that in plus 1 was contained in in, they're really strict inequalities. And if they're strict inequalities, what this means is that the sequence of open intervals is also nested in this case. And if you look at the intersection of these intervals, you will still get that it's equal to the singleton 1, just as was the case in the previous example. But this is not because of the nested intervals theorem. The nested intervals theorem only applies if the nested intervals are closed intervals. In this case, it's a coincidence that the intersection of a bunch of nested intervals ends up being this singleton 1.